welcome to the first lecture of today's program at the 2020 Virtual Heidelberg Laureate Forum. The lecture today will be given by Professor Shigefumi Mori. I will be moderating the session. I am Dr. Tom Crawford. I'm a mathematician at Oxford in the UK, and I also do lots of things on YouTube, in case you vaguely recognize me. I have my own channel, Tom Rocks Maths, and I also do lots of things with Numberphile, which of course is much bigger. So it really is a great pleasure today to be introducing this talk on algebraic geometry from Professor Mori, as I teach some very basic, and I mean very basic, algebraic geometry myself to some of my students here at Oxford. So of course, I imagine Professor Mori's talk will be very much more advanced than the stuff I'm teaching to my first and second year undergraduates. But it does mean that I'm very much looking forward to it. So the speaker, Professor Mori, as with pretty much every speaker, let's be honest, at the Heidelberg Laureate Forum, doesn't really need an introduction. But of course, I will give you a very short one. So Professor Mori is based in Japan at the University of Kyoto. He completed his PhD there in 1978. And then following several visiting professorships across the US, including Harvard and Columbia, were a couple that jumped out at me, he then became a full professor at Kyoto in 1990 and has remained there for the past 30 years, carrying out more fantastic work. He was awarded the Fields Medal also in the year 1990 for his work in algebraic geometry. And the listing describes his important developments, including the minimal model, or Mori's program, in connection with the classification problems of algebraic varieties of dimension 3. So without further ado, I give you today's first speaker, Professor Shigefumi Mori.
Thank you, Tom. So in this talk, I want to explain my experiences from the viewpoint of ideas. So it cannot be a formal lecture. So if you want to ask questions, I can be interrupted, and Tom will take care of it, I hope. Okay, so let me start with my slide. So do you see it, the title of my talk?
Yes. I think so, yes.
Okay, okay. So this is the title, and I want to explain how I became attracted to it and became, after all, an algebraic geometer. So this is roughly the plan. So the essence of algebraic geometry is the interaction between algebra and geometry. I often hear that students in US say that I learned algebra and geometry in high school, so I know algebraic geometry. It's not quite right, but it's almost right. And interaction is between digital and analog. So I enjoy this interaction during the study, researching algebraic geometry. So in addition, I mean, by going further, I'll talk on the comparison between algebraic varieties and modern paintings, because that's the way I enjoy doing research. So I suppose the audience at the youngest, junior or senior in the college, the university, or PhD students or postdoc. So I start my experience in the junior days. So when I was in the third year, a junior, Professor Hironaka visited Kyoto from Harvard, and he gave an introductory course. And so at certain point, I met him in the cafeteria, and I asked him some question, and it was about a non-projective threefold, and this was how it started. So this slide is Hironaka's non-projective threefold. So before that, I learned algebraic geometry by Andre Bell's Foundations of Algebraic Geometry. This is a much older generation, but still I learned it that way. And he introduced complete varieties. Before that, everyone was working on projective varieties. Everything is put in some projective space. And they introduced complete varieties, which may or may not be projective. And I was curious, what's complete varieties? It's not projective. So I asked Hironaka, and he draws some simple pictures. And this was about his example. Let me show you. You might have seen it. Oops. So this is a picture from Hartshone's book on algebraic geometry. So at the bottom, there is a threefold with two curves meeting at 2 points. So if a curve is given, you can blow up. There is a procedure called blow up, replacing a point by a line. And so it's like replacing a point, replacing a curve by a scroll. And since two curves are meeting at 2 points, you can start blowing up one curve starting at the point and another from another point. And somehow the order of blow up changes at these 2 points. So usually you blow up one curve. After you completely blown up, you blow up the other curve. But this time the order is switched. That's all the idea. So you may not be familiar with algebraic geometry, so I just show you the picture. And I don't want to bother you any further. But anyway, the point is that by this simple idea of switching the blow up, he produced a non-projective variety. So almost from any projective variety, he could produce a non-projective variety. So it was quite amazing. And besides that, non-projective varieties, since it's everywhere, and various foundation, this complete varieties gives us a larger category. And I'm not saying that projective varieties are not interesting. It's like classical paintings. After modern paintings are introduced, we can enjoy classical paintings more. So there's nothing of a competition. Okay? And so using these non-projective varieties, we could understand projectivity much better. Okay, so to me, when I was a junior, non-projective complete variety seemed like modern paintings, well, at least to me. And another point is that it was a very clear geometric idea, nothing like a messy computation. So I was very much attracted to that. So that's the essence in algebraic geometry. Of course, in mathematics, we check everything after all by logics, by computations or by logics. But since we are sure of that, we can be very imaginative or wild even. Okay. So this was when I was a junior. Then when I was a master course student or just after getting master's thesis, I was interested in something called catenary ring. So it says a commutative ring is catenary if for any pair of prime ideals P and Q and any strictly increasing chains. So starting from P to Q, always strictly increasing. And prime ideals are contained in a maximally strictly increasing chains. So if P and Q, P is contained in Q, and there may be something else. If there is, you just put in and you make it longer, bigger. And so it says that every chain of prime ideals can be put in a maximal strictly increasing chain and of the same length. Length means counting the number of inclusions. Okay, so this is sort of, if this holds, there is a sort of naive idea of dimension, like a point is contained in a curve, contained in a surface, contained in a threefold. So this way, it gives naively the idea of dimension. So non-catenary ring, if it exists, should have two maximal prime chains of different lengths. So from P to Q of length n, and from P to Q of length m. Of course, one can discuss the definition, but I had no idea how to attain such a situation, such an example. So it wasn't easy to create an example. But again, out of very, how to say, geometric idea. So this is Nagata's non-catenary ring. So he constructed the non-catenary Noetherian local ring. The idea is the following. Here is a curve and here is a surface. You somehow weave them. Okay, so there is some object which looks like a surface on one end and looks like a curve on the other. And somehow you bend it so that the curve goes through a point on the surface, say, call it P. And this is the picture XP. I call it XP. Then XP times affine space, m-dimensional affine space and zero gives a non-catenary example. I mean, I do not give the proof, but you can see that on one side, it's a surface. On the other side, it's a curve. So this sort of unmixed, this sort of discrepancy is a source of the non-catenary ring. See, this is the kind of idea I was attracted. So it's a very wild picture in his mind, but somehow I asked Nagata how he came up with the example, and he said that he just considered 2 points putting together, and he could thought of using it. But I wasn't satisfied, but this is all I could get. Okay, so these when I was in the master course, just finishing master course. So I was just talking about someone else's results only. So I should tell you what I was doing around that time. So this is my master's thesis, weighted complete intersections. So I mean, I guess in my talk, I do not really explain the definitions. I mean, there is a procedure in algebraic geometry to go from commutative algebra to a variety called the spectrum. And also, there is a procedure to go from graded ring to a projective variety called the PROJ. The previous one, spec is very precise. It doesn't lose any information. But the second one omits some data. So it happens when the graded rings is generated by variables of various degrees. If all variables of degree 1, it's a very standard. But when some has a bigger degree, then there is some discrepancy. For instance, it says PROJ of k x2, x3. x2 means x2 is of degree 2. Subindex is means a degree. So PROJ of polynomial ring generated by x2 and x3 is the same as PROJ of x2 cube and x3 square, and it becomes P1. So using different weights has any effect, has no effect. So I was curious, and in that sense, weighted complete intersection come from graded rings with least loss of data. I will not make it very precise, but example is x1, y1, x2, x3. So degree 1, 1, 2, 3, and of degree 6. The opposite is the following. I also studied the factorial graded rings with largest loss. Of course, this the previous one, x2, k, x2, x3 gives the same as usual x1, y1. And so there is some loss, but here is an example, kx2, x10, x15, modulo equation of degree 30. It's a graded ring, and it's a unique factorization domain, whatever it means. And it contains k x6 to the fifth and k10 to the third. So by going to the approach of the previous one, you lose much of information, and it's like approach of kx6 to the fifth and kx10 to the third. So this sort of gap, in going from the graded ring to projective varieties was one feature I was interested in. So we can really get interested in various stuff. And so this is one of the things I was interested in. So later, I worked on a question called the Hartshorne conjecture. And in the process, I could prove the existence of a rational graph. And this was proved somehow very quickly, but still quite amazing. I couldn't improve it much further. So the statement is the following. Let X be a smooth, complex projective variety, and the anti-canonical divisor minus kx is ample. Then X contains a rational curve. So before the theorem, the existence theorem was very specific, like hypersurface in such and such projective space of such and such degree contains a line, that kind of statement. But this is very abstract. And the proof is also very abstract. So the proof needs an argument. Now it's called the bend and break. And it goes to characteristic P, even though the original statement is for complex variety. So the original statement I wanted to prove was Hartshone's conjecture running a smooth projective variety with ample tangent bundle is isomorphic to the projective space. So this is this can be a complex variety of characteristic P, but the proof took place on a scheme over Z. So to me, I was like working on a scheme over spec Z. So if you are not familiar with the spectrum, here is. So at the bottom, there is spec Z. It's just a set consisting of prime numbers, 2, 3, 5, 7, and say P and all the way, and also 0. 0 is a prime ideal. And above it, so this is this is what I borrowed from Mumford's book on projective line over Z. And so over every prime, there is a projective line in characteristic P. And over prime ideal 0, we have we have a projective line over rational numbers. And the idea is that starting from a variety in characteristic 0 over Q, we can sort of specialize it to various primes, 2, 3, 5, 7, and as many as you want. And and I could starting with a problem of a characteristic 0, I go to characteristic P and I use Frobenius and I produce some rational curve and bring it back to characteristic 0. I mean, originally, of course, I did not particularly intended to do so, but it just happened to be that way. So, so this is the Grothendieck's scheme. So I could prove bend and break only on the picture of infinitely many primes. So I don't push my idea to you, but this resembles to me Monet's series of paintings. So in Mumford's picture, he sees many primes, and Monet's cathedral series of cathedrals. He drew cathedral in various timing, like in morning light, in cloudiness, or at sunset. So the idea is the following. Grothendieck tried to understand equation, but he couldn't fully understand it just over Z. So he went to all the primes. So he thought that by going through all the primes, he may be able to get something. And Monet wanted to paint light, which is not paintable. But to capture the light, he drew cathedral in various timings. Again, explore a little bit. So this is Claude Monet. So he painted unpaintables. So he said, to me, an ever-changing scenery does not exist alone. It is given life by the environment, including atmosphere and light. It is only the surrounding environment that gives true value to the object. So he drew paintings like Impression, Sunrise. Impression Sunrise is one picture. Haystacks, Rouen Cathedral. So this is haystacks. So he drew it in various timings. And this is a cathedral I just showed you. So the idea is that by drawing the cathedral at various timings, he could see you can see the effect of the light. And by that, you can understand light. That's the idea. Any questions? So the idea, so I got the idea of bend and break, and I want to develop it further. And so using the rational curve, I tried to apply it. And later, I realized where to put them to examine the situation, to put it in the space of 1 cycles. So this is the cone of curves. So it's a vector space spanned by a class of curves. So it's originally introduced by Hironaka and Kleiman. So in a vector space, a class of a curve is given as a vector. And given a variety, it has so many curves and so many classes of curves. They are converted to a vector, to vectors. And we consider the cone spanned by these vectors. And so this is a cone of curves. And by cutting by a hyperplane, not going through the origin, just to save 1 dimension, this is section. And you can see that on the left side of this line, on the left side of the line, there is some edges or ridge line. And ridge line is called an extremal ray. So my theorem out of bend and break is on the left side of the hyperplane. So I have to explain what this is, but let me skip it. On the half space of this cone of curves, there is always a ridge line, and it's called extremal ray. And so given algebraic variety, I can pick up extremal ray, and each extremal ray represents some geometric feature of the original figure, original algebraic variety. So it's like this. You see, algebraic geometers. So this is algebra. This is me, algebraic geometer, and this is algebraic variety, which is not which you cannot really see, but still we draw something. Something is invariant, and so invariant is in this sense similar to abstract paintings, but unlike arts, we need objectivity and reproductivity. Anyone must write the same picture. So it's different from art, but still it's similar. And to draw unseeable thing by something seeable is like cubism in painting. So here is an example of Paul Clay's picture. He said, art does not reproduce what one can see, but makes seeable what one cannot see. So this is a picture of a steerable grandfather. You can see the meaning. You can see a grandchild sitting on the shoulder of a grandfather and try to steer. But these are made of simple figures, circles, triangles, and so on. And you can examine what the meaning of this triangle, and it may mean something. It's like extremal ray. So this is a very, very short introduction of extremal ray. And from the extremal ray, there are a few directions I went. The classification of certain varieties. and varieties of non-closed fields and minimal model program. And so these are interesting applications. They had the interesting applications because they had some interesting geometric background, this cone. So I have to go, I can, and your direction, Tom.
Yeah, thank you very much. So I think we are going to give you a virtual round of applause. I don't know if this can, and I'm also clapping as well. That was fantastic. Thank you very much, Professor Mori. So this now brings us to the Q&A section of the talk. So we do have time for a few questions. I've also been informed that we do want you to turn on your video as well for the questions. So if you do have a question that you would like to ask Professor Mori about his talk, about his work, or anything in general, I suppose at this point, then do let us know, and we'll be able to turn on your camera, and you'll be able to ask Professor Mori your question. Whilst you're hopefully thinking of all of your fantastic questions, I do have a question for you myself, if that would be okay. So I really enjoyed the way in your talk that you use lots of visualizations of what you were talking about, and you even discussed yourself as a master's student and sort of how you got into algebraic geometry through some of you gave examples of some of the pictures or the diagrams that you saw and thought, that really helped to motivate you to want to study that particular area. Do you find, or when you're working, do you find visualizations particularly helpful yourself in terms of understanding concepts?
So once, usually my answer is yes and no. There are cases it helps. But on one occasion, I was working on something called algebraic stack. And I proved some theorem. And when I was proving it, I thought I went down to the bottom of the problem, and I think I proved it. But then I realized that it's like some picture of a Picasso looking at the woman from two directions put into one picture. And algebraic stack is something similar. So algebraic varieties made by pasting basic algebraic varieties. But algebraic stack is something which you almost paste, but not completely. So this is like Picasso's picture. Yeah, so a face, two sides of a face in the same picture. Yeah. So then the effect is that after that, I started liking algebraic stack and also Picasso's picture. This is a good byproduct.
Well, that was going to be as a follow-up question, in fact, then, like you mentioned lots of artists and paintings in your talk. So is art a particular passion of yours? Are you sort of somebody who's very interested in that?
Well, actually, I don't have much talent in art. So my wife likes those kind of things, and she took me to those exhibitions, and I followed. But from time to time, I got really curious, and the statement of clay was something I found in the exhibition. So I appreciate my life.
Yeah. Right. Do we have any other questions from anybody currently joining us in the chat? Anybody who would like to ask Professor Mori a question? You can turn on your video and unmute yourself, and hopefully you should then be able to ask your questions. Seems everyone's being particularly shy.
Have you found an example where some result or something that you found in the mathematics helped you understand a new perspective on some other non-mathematical aspect of life in a deeper way?
Say it again. Sorry. Could you please?
Have you found any examples where your understanding of the mathematics and the way that things relate to each other in that mathematics has helped you to understand something more profound about a non-mathematical aspect of life?
Oops. Sorry, I'm not yet. I hope to have such an experience sometime. So, but not yet.
Aside from art, perhaps, it does sound as though it perhaps has developed, allowed you to develop a new love or appreciation of some of these artists.
But you see, the point is that comparing art and some theory, I like them better.
Yeah.
That's
Okay, and then we've got a question in the chat, which I will just read out. So this is coming from Alejandro, and Alejandro has asked, could you recommend a book to become more attracted to algebraic geometry? So do you have a favorite text that you might recommend to an aspiring student?
Well, again, this is a difficult question, but I have a deep respect for Miles Reed, and he once mentioned Nagata's this non-catenary example. So I think he has the same sort of feeling I have, like and dislike. So his book should be interesting.
Thank you. Yeah. Oh, and we've got another one from Simon. So Simon has said, this is a rather technical question, asking how far can we go in classifying Fano varieties with the extremal ray approach? So how far can we go in classifying Fano varieties with the extremal ray approach?
Who is Simon? It sounds very technical.
I mean, you mentioned on your last slide that we can use the cone of curves and extremal rays on it in classifying Fano varieties.
Okay, I see. Yeah, so for smooth Fano threefold, I and Professor Mukai, we really classified Fano threefolds by this information. Yeah, so it is possible, but as dimension goes higher, the case is increases so too fast. So I don't know if there is any feasible classification in higher dimensions. And also in dimension 3, when singularities come in, it's can get very complicated. And there is also already very serious and extensive research going on Fano threefolds with something called terminal singularity. So in that sense, my answer to your question is yes for threefolds. But for higher dimension, it's just so many.
Is it not feasible, or is it just not an invariant that distinguishes them?
Well, so in case of Fano threefold, smooth Fano threefold, there are about 100, slightly more than 100. And for fourfold or higher, there was some number of even toric ones, but more special ones. But then it goes to thousands. So even if the classification is done, I don't know how to publish it. Yeah.
Okay.
Thank you, Simon. As you said, definitely a technical question, but an interesting one nonetheless. So thank you very much. Right, so I think that's probably a good place to close the discussion for this particular talk. So the program of events today, of course, there's a little break now and then it will continue in a few hours. Well, I will also be moderating. So if any of you will be coming back to some of the later events and talks, I'll see you then. So again, if we can just thank Professor Mori once again with our virtual round of applause. Yeah, I can see other people clapping. Thank you very much for a really fantastic talk. And hopefully see you all again later today.
Bye-bye.
Bye-bye.